And the last class we have seen the introduction to the orthogonal set. And why do you want an orthogonal set is that only if you have an orthogonal set you can have a Fourier series. That is the reason. Suppose if you don't have an orthogonal set, you just forget about that. There is nothing like Fourier series. You can't have a Fourier series expansion if you don't have a orthogonal set. So it is very fundamental there. Okay, so that's the point. And then let us now discuss what is that we want to do in today's class. The last class set that we have written like this, we have written down like 1 comma cos nx comma sin nx. I don't have to write down cos 1x, cos 2x, cos 3x, etc. because this nx will take care of everything when n is running from 1, 2, 3, etc. And the point to be noted is that n starts from 1 only, 0 is not included. And the reason is, the reason will be clear, of course, there is nothing difficult. In case if you believe that n equal to 0 should also be included, then what happens to the set? You just check it out. If the set will happen like this, if I am going to substitute n equal to 0, this term becomes 0. So therefore 1 comma cos nx comma 0 will be the set. That means inside the set you have 0 as the element. If 0 is one of the elements, then what happens is, this is your last class work, the condition for the orthogonality. We have seen there are five conditions we have seen, right? So one of the 5 conditions, if you see, this is one of the conditions where integral of sin nx and multiplied with cos mx should be 0. By definition it has to go to 0. But now what happens is, if 0 happens to be one element inside the set, then this particular term will be 0 automatically. That means the element itself is 0. When the element itself is 0, what is there to demand that 0 should be the answer? There is nothing to demand. When this is 0, it is straight away 0 only. Therefore, orthogonality property cannot be demanded. Without even demanding, you get 0. So no, that should not happen. So, okay, this 0 should come because of the property only. Okay, otherwise there is no point in discussing. For that reason, what happens is 0 should not be acceptable inside the set. That means 0 is not an element belonging to the set capital S. So that is the point, you keep it in mind. This is one point. And second point is that in the last class we have also seen that the range means from some value to some other value. Between that range we are going to consider some function, and then we are going to make the situation that the function will repeat itself, okay, between that range. That is called a periodic function. I have written here the periodic function. So for example, sin x will be periodic after 2 pi of period. So that is quite trivial. And like that, what happens is that there is no guarantee that every time minus pi to plus pi will come. Okay, in many situations anything can come. So you can have any L here, so minus L to plus L, so that it could be anything. Later we can see, depending upon situation, what is L there. So in general, I am not interested to fix the minus pi here, but rather I would like to make a generalization where rather than pi, let it be anything L. That's the point here. So minus L to plus pi L will be the range, which means 2 times L will be the period. Period equal to minus L to plus L. That is nothing but 2L. So this is what is a generalization. In order to do that, there is nothing much to do. This nx has to be replaced by nx multiplied by pi by L. So you can easily, there is no difficulty here because nx is there, there is no change. Then what is this pi by L? Suppose if L happens to be pi, then L by pi you can cancel. That means it becomes just 1. So therefore nx is nothing but nx only. So nx will be replaced by nx multiplied by pi by L, so that you can consider any arbitrary range. Okay. So now the question is that where is nx and where do you want to replace? So the answer is here. The nx is here. So you see the nx coming here, nx coming here. So these two nx will be replaced by n pi x by L. Okay. For reading, nx into pi by L may be difficult to read. Therefore, let us read like n pi x by L. So that's what I have written here. Cos of n pi x by L, comma, sin of n pi x by L. So this is the one-step generalization of the corresponding or the underlying basis set that we are going to have. The set is also known as basis set. And now we will see one more important condition. Orthogonality condition we have seen in the last class, but that condition has to be supplemented by additional condition. Okay, you should not stop what we have done in the last class. In the last class, we have written down 5 of these integrals, and we have said that all the 5 classifications should be 0 by definition. Okay, this is by definition, and on the left hand side you have to perform the evaluation and verify whether it is really 0 or not. So these are the 2 jobs. Left side you have to perform the actual integration and then verify whether it is 0 or not. Only if the verification happens to be true, only then you accept that this particular set is a valid set in order to proceed further for the Fourier series. Otherwise, you simply reject the set. So that is the point. And now, so starting from here, we are now moving to this little bit generalized situation where the validity range is from minus L to plus L. So this is the first point. And in that particular situation, these integrals can also, the yesterday's integral can also be slightly modified. You see what is the slight modification? You have an integral minus L to plus L. So this is the small modification. Yesterday we have written pi to minus pi to plus pi. Now you write down minus L to plus L. This is one modification. Second modification is this nx goes to n pi x by L. So you can write like this: sine of n pi x by L. Then you have cos of m pi x by L, then multiplied by dx. All that should go to 0. So that's all. So the equation is same only. Only this replacement will help you to move from minus pi to plus pi to minus L to plus L. If these letters are looking very small, then you zoom in your Android device. And so these are the orthogonal conditions. Now what we are going to see is something extra. Here I have written here some extra word. This is an orthonormal condition. So normality condition means that sometimes it must be 0 and sometimes it should not be 0. So these are 0 conditions. And now we are going to see under what conditions 0 should not be there. So that is your second condition that we are going to have. And let us see the first one. Let me write down, rather than writing first one, up to this we have done 5 equations in the last class. Okay, 5 conditions are over. So today's condition I will write it down as 6th condition. So condition number 6 is the orthonormal condition. It is very simple. Orthonormal condition means you square each term. You take any element in this particular set and then square it. That's all about it. And you see this, you forget about this. Okay, so this is over. So let us not worry about this. So we have already generalized the situation to minus L to plus L. So 1 is one element. Cos of n pi x by L is n number of elements. Sin of n pi x by L is n number of elements. Now you choose any element and then square it. So how do you do it? For example, if I am going to take 1 as the element here, I am taking 1 as the element and then I am squaring it. And then the limits should be minus L to plus L. Because of this reason, so you write down minus L to plus L, and that's all about it. And then dx. If you do this, this is called orthonormality condition, and then you have to evaluate this. And let us see how to evaluate. This 1 square is 1, then you get a dx, and you can see that 2 times L is the answer. So what you understand from this integral is that if I am going to square an element here, the answer is 2L. And you also note that L is not 0. You cannot have 0 here. If this is 0, then minus L is also 0. Okay, so that means there is no range at all. So 0 is not acceptable. Therefore, 2L is non-zero value. So that is a point that you have. So 2L is non-zero value. Why I am emphasizing this point is that in the yesterday's class where we have seen the orthogonal condition, 0 must be the answer for the integration. Now, non-zero should be the answer for the orthonormality. So these 2 conditions, if you merge, these 2 means what are the 2? One is the orthogonal condition, and today's discussion is normality condition. If orthogonality and normality is combined, we are going to get orthonormality condition. So this is known as orthonormality condition, and we say that some non-zero expression should come. And similarly, so see, this is the 6th condition. 7th condition, what you will be having, it is integral, once again similar, minus L to plus L. Okay, now let us take the cos square, because cos n pi x by L is there. So let us take cos n pi x by L. So cos n pi x by L is one element and we are going to square it. So if you square this, then I will be getting cos square of, let me write down here, So this is cos, or I will write the whole square here. So it is cos square of n pi x by L. Then you get the dx here, and you can evaluate this. The evaluation of the integral of cos square x. Okay, so cos square and sine square can be evaluated using this expression. You cannot integrate using square, so you have to convert it into 2 times of x, and then perform integral left side means perform integration right side. So essentially you are going to perform the integration for only cos 2x. So the integration part is very elementary, so I am not going to do that. So if I am going to do this integration, you will be again able to show that this is equal to L. So my point here, what is that I am trying to explain here is that if I am going to square an element and then perform the integration, I am going to get some value here which is not equal to 0. That is very important. So let me once again write down, this is not equal to 0. So 6th condition is clear, 7th condition is clear. We have only one more condition, because 1 is over, cos n pi x by L is over. We are left out with sin n pi x by L. So let us do it for sin n pi x by L, and then we can make the conclusion. So let me therefore do the integration for the sine square. So condition number 8. So we have the condition number 8. So integral from minus L to plus L, and take this one, sine of n pi x by L. So sine of n pi x by L, and I am going to square it. So n pi x by L, then dx you have. We have to perform the integration, and here you see sine square function is there. How do you integrate? You rewrite like this, and then you perform the integration. If there is a cos square here, there is a plus here. That's all. There is no big difference. If this is cos square, you put a plus. So integration is therefore very similar. So this integral you have to perform, and then again you can easily verify that the value of the integral is L, which is not equal to 0. So ultimately we have now how many important conditions are there? Yesterday's class 5 conditions, all are 0. Yesterday's class is all 0. Today 3 conditions are there, all of them are non-zero. So there are 5 zero conditions and 3 non-zero conditions. If you combine everything, that means 8 conditions together, then the conditions are known as orthonormality condition. That must be okay, not optional, that must be satisfied for the set S, which is under consideration for the Fourier series. This is a very important conclusion. And the value L, so the value L, how it comes, that is only hardly, it is only 4 steps you can do this integration, and you can get it by elementary integration. So that is not an issue. Now let me actually go into the Fourier series. What do you mean by Fourier series, and where this L is going to come? Okay, let me therefore slightly modify these equations. So 6, 7 and 8. I am going to modify 6, 7 and 8, and then I will write down here after erasing this. Okay. So I have rewritten equation number 6, 7 and 8 in a very small modification. What is the modification? You can see the answer, or with on the right hand side I need to have 1, 1, 1 here. But you remember what was the value for the integration? It was capital L here, it was capital L here, it was 2L here. Okay, you must have written on your notes, so you will be having, even though I erased it. So it is supposed to be a capital L here, but I am writing down 1 here. Then what happened to the L? It has been taken care by writing here. So the L has gone here. Similarly, the answer should be L here, but I want 1 only here. Therefore, the L has gone as 1 by L. Similarly, here it was 2L, but I want only 1 here. Therefore, this 2L has gone to the 1 divided by 2L. So that's the rewriting that we are going to have. And what you will ultimately understand here is that this is a constant term. As you can see that this is the constant term. This is the term that contains the sine, and this is the term that contains the cos. Okay. So only point that you have to remember in this is that only the constant term has an additional 1 by 2 coming into picture. Okay, additional, what is that additional to? Just for information I will write down 1 by 2L. How do you write is 1 by 2L is nothing but 1 by L and divided by 2. So why I am writing like that is 1 by L, this is 1 by L, this is there is a 1 by L here, there is 1 by L here. Then what is this is actually this amount divided by 2. So that is what you understand here, which means for constant term only there is an additional divided by 2 is there. So that point only you note down. So, okay, only for constant term. For the sine and cos term, you don't have the additional divided by 2. Okay, so with this, what is that we are planning to do here is that the plan is like this. So we are going to consider some periodic function f of x. So let me write down that the function will be like this, 2 pi. For simplicity, 2 pi I am writing so that you can easily consider sin x, cos x, etc. So the period is 2 pi. So what do you mean by periodic? This is the condition. Periodic means, mathematically speaking, this is how you write down. But if you want to see on the CRO or a digital storage oscilloscope, you can always take the output from the signal generator and give it to the CRO. You can see the sine wave and cos wave, and you can see that this sine wave will repeat itself after a period of 2 pi. So you can visibly, you can see it, or mathematically you can write down equivalently like this. So we are going to consider periodic functions that are looking like this. And in particular, it can be 2 pi. In general, you may not expect every time 2 pi. So we can always write down like 2L here. So that is how you write down. So f of x here. In general, okay, if it is not a sinusoidal function, probably the range may not be matching with the 2 pi, in which case you can write down 2L is the period. So that is the idea. And now, what is the overall idea and the connection between the Fourier series and this orthogonal set is that this particular function, okay, this right hand side I will remove. Now you can ask the question, why do you want to write like this? The moment you write like this, we understand that this function is periodic. That's all about it. You don't have to write, so in the English word I am writing periodic function like that, there is no need to write. The moment you write down that f of x equal to f of x plus 2 pi, that means that the function is going to repeat after every 2 pi. So that means it's periodic function, and therefore that is everything is implied. So we are going to consider only periodic functions in the sense that in the signals and systems, because most of the cases, what is the practical application of this Fourier series is in signals and systems where some kind of signal will be repeating after some time. Okay, some signal like this will be there, and the same thing will be repeating after certain interval. So if that is the situation, we are going to have periodic functions, and for periodic functions you can write the Fourier series like this. That is the meaning here. So this is what is that we have written on the left hand side is a periodic function of any period. Period doesn't matter, any period is okay. Some period is there, I have a periodic function. This function can be written down as a constant plus several sinusoidals. Okay, so that's all about it. So what do you mean by this is that we are trying to say that you give me any periodic signal, okay, arbitrary, okay, there is no proper shape for that, arbitrary shape. Then if you give like that, then Fourier says like this is a mathematician, no? He says that this is equivalent to a constant signal. In signals and system, we say it is DC. Okay, on a CRO, if you are having a signal, if you are going to have a signal like that, suppose if you are going to have a signal like that, then this constant will be, it will be shifted up here, so it will be coming here. So this particular sine wave will go here, and that is the effect of the constant. So it can go up here or it can go down there, depending upon whether this is positive or negative. So the effect of the constant is actually the effect of DC. It is called a DC signal. So DC signal will go, it will be shifted up and down. AC signal only will tell you what is the frequency, etc. So the effect of the constant is only to little bit shift up and down. That's all about it. So that is a constant. Then plus several sinusoidal. Sinusoidal means a combination of sine and cos. Okay, forget about square here. We are having the set, right? So we have a set here. The set is equal to 1 comma cos of n pi x by L. Then you have a comma sine of. So what do you understand and what is the set now? You see constant is there, 1 is there, several is there. Okay, several means n equal to 1 2 3, n equal to 1 2 3 etc 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 go up to infinity, that is okay. So infinitely many, several means infinitely many. Sinusoidal means a combination of sine and cos. So a combination of sine and cos including any phase, everything is included. That kind of combination is called sinusoidal. So ultimately you understand the connection between a Fourier series. This is called a Fourier series, and this is your underlying basis set. Basis set is very important. If you don't have this basis set capital S here, you cannot write down the Fourier series. Okay, so that's a very important point. So now the point is now clear, that the purpose of the constant is now clear. It's only shifting the entire signal up or down by a constant value. That is called a DC component. These things are called the AC component, and you know that this n into pi by L, you can always calculate the frequency. N pi by L, you can calculate the frequency. Okay, if this is cos of omega x, then omega is the frequency. So, and when omega equal, as you can see that n pi is there. So n pi means, let me write down clearly, n pi x by L is there. So when n equal to 1, you have pi x by L. When n equal to 2, 2 pi x by L, etc. These are known as harmonics. Okay, higher frequencies means harmonics. So this entire combination plus a constant will give you any arbitrary signal. The power, you see how much powerful this equation is, that this is not a particular signal. So okay, this is any periodic function. So in mathematics we can most probably we use the word arbitrary. Okay, arbitrary periodic function. That means you give me any signal which is periodic in nature, then we can decompose it into only in terms of sinusoidals. The DC part, as you know, that it's only shifting, so nothing will happen to the original structure, and so the entire thing is decomposed into only sine and cos. So you see any means arbitrary. Arbitrary means infinitely many combinations. Okay, you cannot even classify how many varieties of signals are there. Structure wise, I'm telling. Once you draw a particular shape, okay, and you cannot classify that this many varieties of the signals are there. Okay, too many varieties are there. But even though you have too many varieties of the signal, the whole thing is decomposed, or it has been brought down to only sines and cos. Only sines and cos. Therefore, what happens is, in signals and systems means practical application of signals. In system means some engineering design, or you have a machine that's called a system. That system will analyze the signal. That's called a spectrum analyzer. Spectrum analyzer means the system will analyze what is this periodic function is all about, and it will analyze and it will tell you how many cos and how many sine waves are there with what frequencies. Okay, it will give you what are the frequencies, and therefore your time, this is a time. Generally what happens is, practical situation, this is time that you will be having, and this time will be converted to the frequency. So time domain will be converted to the frequency domain. In the frequency domain, it is called spectrum. So that is why in practical electronics lab, you will be having the so-called spectrum analyzer. So spectrum means we will be getting the frequency components of the input signal. Usually input signal will be a function of time. So time will be converted to the frequency. That's what is doing the spectrum analyzer. So the whole lot of mathematics is going on inside that electronics, and this analysis is known as the Fourier analysis. Now let me therefore write down for clarity, rather than writing like this several sinusoidal, I would like to write down how the entire equation is going to look like. So any arbitrary function or periodic is very important, periodic function can be written down like this, a constant. So constant is what I am going to represent by a0 by 2. And now you can understand why the 2 comes into picture. Constant will have an additional 1 by 2 factor. That's what I told you here. This is a constant term, this is the sine term, that's a cos term. Only for the constant term an additional 2 is there here, additional 1 over 2. So that is why for the constant term alone you have to put a 2 here. Then plus several sinusoidal. Several means how many? Infinitely many. Therefore I will write down n equal to 1 to infinity. Infinitely many. Sinusoidal means cosine also, sine also. So therefore I will now write down that this can be some constant into cos of n pi x by L. That is for all those combinations. Then plus, and what about sine? So similarly you write down n equal to 1 to infinity. A different constant, this is an, so that is a different constant. Then you write down sine of n pi x by L. So this equation is starting here and ending here. So there are 1, 2, 3, 3 are there. In that, this is actually infinitely many terms. This is also infinitely many terms, and then one constant term will be there. If you write like this, it's okay. So this is this RHS is the Fourier series. Fourier series of f of x. It is also called a Fourier series expansion because you have infinitely many terms here. So the overall idea is just now clear, and where the constants are there, a0, an and bn. Constants can be determined easily, that's not a problem. And how you can determine is because of this property. Now you understand why there should be 1 here and why there should be 0 here. Okay, only because of this 1s and 0s you will be able to calculate the constant an. An means what? An means a1, a2, a3, a4, etc. When I substitute n equal to 1, 2, 3, 4. Okay, a1, a2, a3. Similarly, this will be b1, b2, b3. This will be a0. So how do you calculate this constant is because of the properties. Once for the equation 7, equation 6, 7, 8, and then 0 for equation number 1, 2, 3, 4, and 5. If you don't have those zeros and ones, you cannot calculate these constants. So that is where the orthogonality property comes into picture. The determination of the constants is because of the orthogonality property. Okay, that is the point to be noted. And now you understand what is meant by Fourier series. The purpose of the Fourier series is to decompose the given signal. I have a signal which is very complicated. I am unable to understand. So when something is too much complicated, I decompose. When I am decomposing, how many varieties I am decomposing is only sine and only cos. But you may say that infinitely many. Infinitely many is okay. But one of them will be sin x like this. It is sin x, sin 3x. So sin x, sin 2x, sin 3x, sin 4x will be coming. So if you understand what is sin x, you can also understand what is sin 3x. So therefore what happens is, if even though there are infinitely many, they are all higher harmonics. Okay, sin 3x is the higher harmonics of the sin x. Similarly, cos 3x is the higher harmonics. So therefore, you are actually getting higher harmonics of sines and cos. As long as you understand the properties of sine and cos wave, you understand actually the complicated signal. So complicated signal can be understood if you understand what is a DC signal, and if you can understand how a cosine signal will behave, and also if you understand how a sine signal will behave. So only if you know DC signal, sine signal and cos signal, you can understand a very complicated, infinitely varieties of complicated signal. This is called the Fourier analysis. So you are actually analyzing a complicated signal in terms of simple DC and sine and cos waves. Okay, so that is the very powerful technique, and that is the reason why the entire technique is used in a title called Signals and Systems. For most of the time, BTech students will be doing that course. Okay, we will take an example, and then I will tell you in the next class how to calculate these constants an, bn, etc. that we will do in the next class. Okay, bye.